Assalamu alaikum. Bismillahirrahmanirrahim. Today we discuss MPLS second module. I think let's go for let's go to learning portal. In courses service provider routing and switching JNCIS-SP. Oops. Okay, so our module is Junos MPLS fundamentals. Today we discuss module 3 MPLS the mechanics. MPLS the mechanics. Okay, so let's start our today's topic, MPLS fundamentals. And in MPLS fundamentals, we are discussing today basically 5 sections. In MPLS, the mechanics, the section 1 is the structure and MPLS label. Second section is MPLS router roles and label actions. Third section and data plan across a label switch path. And number 4 is implicit null and explicit null and reserve labels. And last one is the MPLS transfer protocols. So go to first the section 1, the structure of an MPLS label. Okay. So this is the some terminology which is used in our MPLS session. Number 1 is LSP, label switch path, MPLS, multi-protocol label switching, LSR label switch router. P router means provider edge router, C router, customer edge router, P router means provider router, PSP means penultimate hop popping. So this is the key word or terminology or short name which is discussed in our entire MPLS journey. So let's start. So first one, what is an MPLS label? So this is the main key or signaling protocol which is running in underlay and where deploying MPLS L2 VPN, L3 VPN over this label. So an MPLS label is just a number in a header. So MPLS label is just a numeric number, and this number is starting from 0 and the ending number is 1048575. Total is 20 bits long. Total is 20 bits long. And in our IP header, that is 32 bits long, 32 bits. The header is 32 bits, but total level is 20 bits. So MPLS header, MPLS header total is MPLS shim header. In left side, and that is Ethernet header, that is layer 2, and right side, this is IP header or layer 3. Header between layer 2 and layer 3, MPLS shim header has inserted. Okay, so someone sometimes called MPLS it's a 2.5. Okay, and this header is inserted between layer 2 and layer 3. That's why sometimes someone called it's 2.5. So this MPLS shim header total is 32 bits long and label is 20 bits. Advertised in a shim header, how are labels generated? Almost always automatic, occasionally manual. You can generate the MPLS label in manually, that is static. Uh, but most of the case, we are using dynamic. It can be happened or it can be by using LDP, level distribution protocol, or SPP or 740. The level often changes hop by hop. It depends on router role. Okay. Later we discuss the router role details. MPLS shim header is inserted between the layer 2 and layer 3 header. Yes. And this is in details of MPLS shim header. So total is 32 bits, 20, 3 plus 1, 4, and 8. 8, 4 plus 8, 12, 12 plus 20, total is 32. So total 32 bits and 22 bits is MPLS level. Number two, TC. TC means TC is 3 bits, S is 1 bit, and time to live is 8 bits. So first one, the structure of an MPLS level header, the time to live, that means TTL value. A counter decreases by 1 at every hop, as like IP header. If a routing loop occurs, the TTL reaches 0 and the packet is dropped. Prevents packets from looping forever. By default, IP TTL is copied to MPLS TTL. By default, MPLS take TTL from IP TTL, basically. So this is time to live or TTL, that is 8 bits. The 3 bit is TC. TC bit means MPLS TC bit. Let's see MPLS TC bit. Traffic class. Traffic class. TC means traffic class. And another one is stack bit. So later we discuss TC and stack. So first one is MPLS label, that is 20 bits. It's just a numeric number. And time to live and or TTL, it's like IPTTL. Which bits are originally known as experimental bits. TC, traffic class bit, basically it's an experimental bit. Okay. Which bit prevents packets from looping forever. That is time to live or TTL. And now we are in section 2, MPLS router roles and label action. That is very important. And this is the terminology basically. MPLS terminology, ingress and egress router. So see the topology. So considering it's a site A and this is the site B. Site A, this router is basically customer router. This router, site A, this basically customer router. Site B, also a customer router. This is location A and this is location B. Customer CE router is connected with PE provider is, that is R1. So I'm considering from left to right. So this router is ingress router and last one router is egress router. Okay. So for ingress and egress router, what is the role uh, in ingress router and egress router in MPLS topology? Just see here, level switch paths are unidirectional, not the bidirectional. So if you considering this is point A, so router is ingress router. If you consider this is the starting, packet is traveling from customer A's router to provider A's router. If you considering your journey start from side B, that will be ingress router, and this one, that is R1, will be the egress router. Okay, that's why the labels which pass are unidirectional, not the bidirectional. If you're considering from site A, router 1 is ingress router. If you're considering from site B, router 5 will be the ingress router. You will probably also need a second LSP in the reverse direction. So some like static routing, you are just giving the forwarding route. You have to maintain the reverse route. So LSP is unidirectional. If you mention LSP from router 1 to router 5, this is one direction. If you want to mention router 5 to router 1 again, then you have to create another LSP. Okay, so that's the point. Labels which paths are unidirectional. So R1 is the ingress router or hidden router. Traffic enters the LSP on this router. And R5 is the egress router, that is the exiting router. Or you can say the tail end router. Traffic leaves the LSP on this router. Traffic in router 1 and leaves traffic from router 5. That's why traffic in router is ingress router and traffic leaves from router 5, and router 5 is called the egress router. So this is the naming convention in MPLS topology. Which one is ingress router and which one is basically egress router. Inter between ingress and egress router, inter between all router is transit router. Inter between all router is transit router. So transit router, router 2, router 3, router 4 are transit routers for this LSP level switch path. They forward a packet toward the egress router, also known as label switching router. Label switching router, LSR router. LSR forward based only on the label. LSR forwards based on label. Only transit routers are LSR in the pure sense. That means ingress and egress router actually forward packets based on their IP address. Ingress and egress router actually forward packet based on their IP address. And purest router is based on label. This router is actually work based on label. But in PE router, they are communicating in IP domain. Here is communicating with MPLS domain. Okay, both is connected with PE router. A router can be ingress for some LSP, transit for others, and egress for others. So one router can be a ingress router, considering site A is the starting point. If I considering site B the starting point, router 1 will be the egress router. So one router can act as a ingress router or egress router. It's basically depends on which point we consider for starting the journey. Okay. MPLS terminology: PE, provider edge router, P, provider router, and C, routers. So this is the naming convention in MPLS topology. So say here, router 1 is the P router, provider edge router. P means provider edge, host customer circuit, external peering or transit links, learn BGP prefixes. This router are the ingress and egress points for an LSP. The policy filtering and manipulation take place and traffic can be sorted into different classes of service. So this is the P router. And P means this is the provider router. Basically router 2, router 3 and router 4, it's a provider router. And this router basically forward their label forward packet based forward based on label. Okay. Router can act as hello. And all time customer S router is connect with P router. Customer S router is connected with P router. Inter between P router, all are provider router. So this also the P router. This is customer AS router, and this three router, router 2, router 3 and 4 is the provider router. This is the MPLS terminology or naming convention. Okay. Routers can act as both PE and P devices, chassis and line cards. The router chassis and line cards can be selected to favor forwarding speed over route table size. Offer optimized traffic manipulation. Some network keep a strict separation between provider and provider as roles. Not always practical in some topologies. Some networks may not have the financial luxury. That means you just consider you have only just a minute. Hello? Ah, okay. So one router can be operated as a provider S and P. That means provider router. So consider in that case, you can just you have only two router. Consider you have only two router. Okay, this is only two router. Your network only two router. So here, which one is provider router? Which one is provider S router? If you say this is provider edge router, so it's also a provider edge router. This provider edge router also act as a provider router. So if you add another router in between this, you can say this is the provider router and this one is the provider edge router. Okay, it's depends on topology basically. So this is the statement. Router can act as both provider S and P devices, chassis and line cards. The router chassis and line cards can be selected to favor forwarding speed over the route table size or for optimized traffic manipulation. Some network keep a strict separation between provider and provider S roles, not always practical in some topology. Okay.
But yeah, one question.
Yeah.
Yeah, you mentioned it previously, IP domain topics. What does that
Hmm.
exactly mean by IP domain
IP
between
domain. Okay. See here. This one is MPLS domain. This router is under MPLS protocol. Okay. And this router is the customer router. Customer router, we haven't enabled or don't enable MPLS. This is normal IP routing. This may be customer communicating with the router one using static routing or using BCP. This is normal IP routing. Not MPLS communication happen between customer S router and provider S router. That's why I called this portion is IP domain. Okay, and this is the MPLS domain, and this is another. It's an IP domain. IP routing is happened here. But in MPLS domain, level switching is happened here. Or level distribution is happened here. Clear?
okay,
Okay. So router can act as both provider is and provider devices, that is transit. So see here router 3. Router 3 is connected. Router 3 is connected with router 2 and router 4. So what is the role of router 2? Router 2 is provider router. Router 4 is also the provider router. Router 3 is also provider router considering site A and site B. If you considering site C, this router is the provider A's router considering site C. So combine. This router role is combined. Provider A's and provider router. Both role is uh, both role will be executed in router 3. So this is the topology when one single router can act as provider is and provider router. P can also act as a transit for other LSP. For site A and site B, router 3 is transit. Router 3 hosts a customer circuit and is also transit between router 1 and router 5. Your choice will bring their own advantage and disadvantage. Make the most optimum choice for the network and the business. And when you're considering site C, this is provider is router. So one router in MPLS domain can act as provider is and provider router, both. So let's back to our ingress router. Considering I'm sending packet from site A to site B, and our site A is the customer A's router, and router 1 is the provider A's router. So customer is sending packet to router 1. Router 1 is the PE router, provider is router. So they are receiving the packet. Router 1 is receiving the packet and inserting or push label on that packet. Push label on that packet in router 1. So you can say router 1 role is ingress router, and this router operation will be push. That means insert label with packet. In this diagram, the CE at site A sends a packet to PE, provider is router. The PE pushes label, this is the label value, onto the packet. R2 told R1 to use this label. R2 told router 1 to use this label for traffic on this LSP. So router 1 inserting this label and sending this label to router 2. Router 2 receiving this label as an incoming label, and this is a transit router. They are swapping the label from this label to another label. That will be happened dynamically if we use label distribution protocol. Okay. So next. So see here, router 1 is sending packet with label. The label value is 876543. Router 2 receiving the incoming label and sending another label. Sending another label to router 3. Router 3 also sending another label. And router 4 not sending label, only sending the packet. Only sending the packet. That means router 4, here router 4 role will be different. Router 4 role will be different. Router 2, the role will be swap. Router 3, the role will be swap. But router 4, remove the label. Remove the label and send the packet to egress router. And egress router also sending packet to customer edge router. So pop operation is happened in router 4. That means remove. Pop means remove. So there is 3 action basically. Router 1 push label with packet. Router 2, router 3 swapping the label, and router 4 popping the label. Okay, this is the 3 action. So here transit router action will be swap. Ingress router action will be push. and egress last egress router, you can say pop router or PSP, penultimate hop popping, is happened in router 4. They This router remove the label and normal packet is sending to egress router. Egress router is sending packet to customer is router based on routing protocol. So see here, each router tells the previous hop which label it wants to receive. The label is swapped as it changes by hop. R2 asked R1 to use label this label. Okay. R3 asked R2 use label this label. Labels are not usually bound to an interface. Labels are not usually bound to an interface. Label automatically generated. Okay. R2 could receive label this one on any interface. Useful for rerouting traffic in times of failure. So this is the basic function when label processing from ingress router to egress router in MPLS domain. How it basically travel.
That means our provider edge router basically generate label.
Yeah. Provider edge router, if you considering ingress router, they are generating the label. Okay. And this label goes up to penultimate hop or PSP router. Then PSP router is removing the label and sending normal packet to egress router. Okay. So MPLS label action, that is pop. Last action is pop. Removing a label is called a pop. Pop means a removing label. So which one removing label? R4 pops the label before sending the packet to router 5. R4 removing the label before sending the R5. No point in R5 looking up a label when it is the final hop in the LSP. That is final hop. That is egress router. This is called penultimate hop popping. This event is called penultimate hop popping, PHP. This is the default behavior of all LSP. So egress router left one is the PHP is happened. Okay, PHP is happened. Penultimate hop popping. In penultimate hop popping, this router basically pop the label and send packet to egress router. So there is basically three actions: pushing, popping, swapping. Pushing, popping, swapping. Three actions based on router roles, basically. Match the roles of the routers in the MPLS terminology. Provider is, what is the role? Host customer circuit, external peering, and transit links. Is provider host only for transit, has no need for BGP or VPN information in provider router. It's basically used for transit. No need BGP, no VPN information. Customer edge router. This is basically a normal router, IP routing router. Host the customer one circuit which connects directly to PE. Which kind of router will transport the packet toward the tail end of the LSP once the label packet has entered the label switch path? That is transit router. So our third section, data plan across the label switch path. Data plan across a label switch path. So this is our terminology and the journey of an MPLS packet. Ingress. Again, see. again host A sending packet to customer A's router, customer A's router sending packet to provider router. Okay, packet ingress, that is part one. So this is ingress router, packet is coming and router one inserting label with packet and sending to router two. So ingress, that is part two. And this packet, after getting this packet, inserting label, then this router swapping label, then this router pop the label, send packet, again send packet, then getting the customer. So this is the entire journey basically. The journey of an MPLS packet, the inet.3 table. MPLS basically use two tables. One is MPLS.0 and another one is inet.3 table. Inet.3 table. And see the details of inet.3. Inet.3 table contains all LSP that begins on this router and see the level distribution protocol. This is one level distribution protocol, RSVP. You can also use LDP or also you can use segment routing for level distribution. Okay. This output shows R1 is ingress to 3 LSP. All LSP are learned via RSVP, Resource Reservation Protocol. And R5 loopback is this one. Uh, our topology will be this. Uh, just show you. Your lab topology will be this one. Okay. So this is router 1, VMX 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Total 10 router is connected with this other. This topology um, will be the lab for MPLS session. Okay. So see. So here we basically discuss about the inet.3 table. And inet.3 table is the MPLS routing table. Okay. MPLS routing table. And your packet is travel or label is travel based on this table. Okay, based on this table. Show route. This is route table inet.0, and in inet.0 will be connected with inet.3 if you configure BGP. Basically, inet.3 table is mm, communicating with inet.3. Only BGP protocol will be communicating, or only BGP can communicate with inet.3 table. No others protocol cannot communicate. See here, using LSP to resolve BGP next hop. When is the inet.3 table used? Default behavior is to resolve BGP next hops used exclusively by BGP. Only BGP will use this. OSPF and ISS never look up this table. Never look up this inet.3 table. Output shows a prefix R1 learned from router 5 via BGP. R5 loopback is the protocol next hop. LSP router 5 can be used to resolve the BGP next hop. Result push level 16 and send toward R2. This is the basically after configuring our lab, we can verify this command. Okay. So number one point you have to remember this inet.3 table. What is the inet.3 table? It's a MPLS routing table, and BGP only can communicate with INET.3 table. Okay, no other routing protocol can't communicate with INET.3 table. Okay, this the statement. Okay, and this verification we can check after lab. Comparing INET.3 and INET.0. So see here one route, show route. This is our destination. So this destination, when you're checking the INET.0 table, we're getting one routing protocol. Routing protocol name is ISIS, and same information is getting from INET.3, and this is getting through RSVP, and this is the next hop, and this is the LSP. So this is the basically structure of INET.3 table and the INET.0 table. This basically packet travel through level switch path, and this INET.0 table is normal IP routing table, IPv4 unicast. And see here, router 1 has a router 5 loopback in both the INET.0 and INET.3 tables. Router 5 loopback is in INET.0 table, also in INET.3 table. Which table wins? Which table will be preferred? In fact, both are equally valid. The route preference decides the winner, not the table. Note, the INET.3 table is preferred in tiebreak. The result around pushes level 16 onto the packet, force it to R2. That means you are getting what prefix says both in INET.0 and INET.3. So INET.3 will be more preferred. INET.3 table is preferred in a tie break.
Sir, is there INET 0 will work with BGP?
INET 0 obviously work with BGP. If you configure BGP, that is BGP for IPv4, BGP all route will be stored in INET.0. Only MPLS, when you configuring MPLS, then the route will be in MPLS routing table. Route will be in MPLS routing table. Okay.
Sir, I have one question here.
Mm-hmm.
Sir, for 192.168.1.5 prefix, the both metric is 40/40, sir. So in that case, router will do load balancer, right? It will share the both INET.0 as well as INET.0, right?
Okay. So see the topology first.
Yeah, only
So
one link is there.
say
So, yeah,
router
in
1
that
to
case, sir,
router
if we
5.
have a two links, then how the route will select, sir?
Okay. Check. See here. This is router 1 and this is router 5. Okay.
Okay.
So see here. Uh, I'm getting this route. Router 5 loopback. 192.168.1.5. Router 5 loopback from
Okay.
router 1.
1.1.
Yes,
Yeah.
from router
Yeah.
1. So this is the shortest path. I think this is the shortest path,
Yes, yes,
right?
correct, sir. Yeah. Yeah, it's correct.
This is the shortest path. Okay. So if you consider this is 10, this is 10, 10, this
1040.
is 10. So the summation is what?
40.
Yes. That's why you are saying 40. Clear?
Okay, okay, sir. Okay, got it, sir.
Okay. I will show you in lab details, in details. Okay.
Yeah, okay.
Okay.
Thank you, sir.
Okay. So if you just you are getting one prefix, you are just checking one prefix. It can be customer prefix or it can be egress router loopback. You are getting to different routing table. This is INET.0 and INET.3. In that case, router 1 prefer INET.3 table, not INET.0 table. So this is the message. Basically, this is the message of this slide. Okay, just remember this one. Okay, the journey of an MPLS packet, that is swap. Swap is happened in transit router. Okay, swap is happened in transit router. So this output shows that router does with level 16. That means there it's an, you can say it's an incoming level, and swap, after swap the level is this, another level. So router 2 basically receive incoming level from left and sending any random level to neighbor router, any random level to neighbor router, or you can say um, in our topology, router 2 is transit router. Swapping operation is happened here. So BMX was sending incoming level. Maybe incoming level is 10. Receiving the incoming level and sending another level to router 3. Router 2 not send same level which has received from router 1. They are changing this level. It can be random. Okay. Just for example, sending level is 20. Incoming level is 10. Sending level is 20. It's an example. Okay. So it's basically this level distribution is controlled by level distribution protocol, basically. Okay. So let's INET.3 and MPLS.0 tables be clear on the difference. Okay. So there is basically two tables. In Juniper, there is two tables in MPLS operation, you can say. One is INET.3, that is MPLS routing table, and MPLS.0, this is MPLS level distribution table. Okay. These two Junos MPLS tables have different responsibilities. What is the responsibility? INET.3 table responsibility and MPLS.0 table responsibility. So first one is INET.3 table. Contains all LSP that begin ingress on a router. So all LSP level switch path will be stored in INET.3 table. Will be used by BCP for recursive lookup. Used on incoming packets with no label. Incoming packets with no label. So this is the INET.3 table. And MPLS.0 table used to look up incoming packets that already have a label and will be used by routers that are transit for LSP. Egress router also use it to look up VPN labels and covered, basically we covered L2 VPN and L3 VPN. When you configure MPLS L2 VPN, MPLS L3 VPN, we can show you the VPN labels and what is the function of egress router and how egress router look up VPN labels. Okay, so here in MPLS domain, there is two table basically. Number one is INET.3, another one is MPLS.0. INET.3 stored basically every LSP. Okay, and this if you configure BCP, so BCP will use this table also. Okay, and use no incoming packets with no label. Used on incoming packets with no label, and MPLS.0 basically label distribution scenario. is stored in MPLS.0 table. So when we configure our lab, then I show you the difference clearly.
That means, sir, MPLS init 3 table actually work with provider edge and client, basically.
Provider is and no, not the client. Client is a client is in IP domain. Okay, basically you can say it's contain all LSP label switch path. All LSP will stored in init.3 table. Okay, not mentioning the customer. Okay. So penultimate hop popping. So penultimate hop popping, we already discussed about penultimate hop popping. In our topology, router 4 is penultimate hop popping, and this router 4 basically pop the MPLS label and send packet towards router 5. So this is the penultimate hop popping. Check your understanding the question 1, which protocol uses the init.3 table to resolve the remote next hops if the label switch path in the init.3 table has an egress point. That is basically BGP, init.3 table. And this is two table, init.3 table and the MPLS.0 table. We already discussed about two table. What does the label forwarding table contain? A label switch path learned by a protocol. The forwarding action taken on a packet with the label is the forwarding label contained. And this section we will discuss implicit null, explicit null, and reserved labels. Some labels are reserved, not used in production. Okay. And two keyword we use, one is implicit null and another one is explicit null. So when we use implicit null or explicit null, and what is the reserved level range? So see, implicit null label. So see here, I'm the final hop. Router 4 is the final hop for label, considering the label. When I say level 3, I mean don't send me a label. When I say level 3, I mean don't send me a label. Don't send me a label. That means, see here, MPLS labels 0 to 15 are reserved for special use. 0 to 15, 0 to 15. Router, don't use this label, 0 to 15. How does router 5 tell router 4 not to use label? It advertises a special label. Not to use label means router 5 advertises one label. The label value is 3. In that case, router 4 don't sending or swapping label and don't send to router 5. So this is the special label, that is label 3. It is never actually added on a packet in the data plan. Label 3 really means pop the label before sending the packet to me. Label 3 is called implicit null. Label 3 is called implicit null. So considering router 5 is egress router. Router 5 sending packet to router 4. Sending packet to router 4. So I'm the last one. I'm the egress router. I'm the last one. So sending packet to immediate router and the label is spatial label value. The label value is 3. This label value 3 is called the implicit null. Implicit null. Okay. And this is happened by default. This is happened by default. Okay. So this is the definition of implicit null label. Basically, there is value, the label value is 3. That is reserved. Okay. So this is implicit null label. That is part one. Some application require label at the final hop on any class of service marking end to end. This is basically service provider might not want to change the customer markings, but want to use different markings in the MPLS setup. The customer intent can be carried to the other side of the network without being processed as a high priority. The result is that egress router receives a plain IP packet with high priority markings. The solution is to use MPLS label all the way to egress router. The tail-end can request explicit null label, level 0 for IPv4. So this is explicit null. Explicit null. That is, explicit null is that tail end can request the explicit null label. The label value is 0 for IPv4. When we receive any label value with 0, that is called the explicit null. Explicit null. And this will happen in tail end, that is happened in egress router. Okay, that is explicit null. See here, I am the final hop. I am the final hop. When I say level 0, I mean use level 0. That is, level 0 indicate that the packet is at the end of an LSP. Immediately tells the final hop. The egress router will always look at the next header in the stack. Level 2 for IPv6, pop the label and inspect the destination IPv6 address in the payload. For IPv4, the label value is 0. For IPv6, the label value is 2 for explicit null. So here 3 value is, we already got 3 value. Level 0 for explicit null for IPv4, level 2 for explicit null label for IPv6, and level 3 is implicit null. So this is reason 0 to 15, and this is the full table. This is the full table. 0 IPv4 explicit null, 1 router alert label, 2 IPv6 explicit null, and 3 is implicit null. And these are the others label value. Router don't use this reserve value for label distribution. Okay. So now we are in question and answer section. Match the labels with their description. Level 0, IPv4. This is basically comes from this table. Which MPLS level informs this router in the path to inspect packet before forwarding router alert. And hopefully this is the last section. The 4 MPLS transport protocols. RSVP, a resource reservation protocol. It's a label distribution protocol. Okay. There are 4 primary protocols that can build LSP. RSVP is the first protocol you will master. You manually create RSVP LSP through some kind of explicit intent. Various methods, but the 3 most common are manually configure one at a time, manually configure through a controller, automatically configure to egress router within a defined range. You still have to manually define the range. So when we deploy in production, manual LSP, basically, we don't choose manual LSP. Okay, that will be the dynamic. RSVP, the advantage. What is the advantage of RSVP? So see here, this is a ring network. This is basically a ring network. So router 1 is starting. One blue arrow is router 1 to router 5. Another red arrow is router 1 to router 5. There is 2 different paths. Okay. So this is basically shortest path. This is basically shortest path. Priority traffic LSP via the shortest path, and best repo traffic LSP via longer path. Okay. So how it will be happened. RSVP offers many useful features. you can engineer is LSP individually. Traffic engineering hop by hop or to avoid tracked links. Verifies protection from faults, bandwidth reservation and LSP with different priority levels, automatic discovery and better path, and route around links experiencing high bandwidth restoration. That means if you implement traffic engineering in your MPLS domain, so you can use RSVP. By default, LDP have no feature in traffic engineering. If you make traffic engineering in your MPLS domain, you have to use RSVP or segment routing. Okay. So this is the advantage of RSVP. Level distribution protocol, that is LDP. This is another level distribution protocol. This names is LDP, level distribution protocol. LDP is very popular choice. LDP is more simple than RSVP due to the fact that it does not offer any traffic engineering capabilities. There is no traffic engineering capabilities in LDP, but LDP is very popular compared with RSVP. Okay. So LDP automatically creates a full mesh of the LSP. Simply enable it on the core interfaces. The trade-off traffic only ever follows the metrically based path. LDP basically use the backend ICP. You are just using backend ICP. You can use WSPAP or ISS. Firstly, LDP use the ICP path. But when you use RSVP can, if you implement any traffic engineering, then your traffic engineer path will be followed. And another one is segment routing. For traffic engineering, you can also use the segment routing. No need another routing protocol. You just extend WSPAP and ISIS. Okay. MPLS segment routing advertise label directly in WSPAP or ISIS. No need to introduce LDP or RSVP. Just you enable segment routing under WSPAP or ISIS. You can use WSPAP or you can use ISIS. But I recommend ISIS. ISIS is more better than WSPAP. No need to run separate protocol, reduces the amount of state that a router has to maintain. Routers have full visibility of every level that every router expects to receive. Headend can push a stack of labels on a packet to send traffic down a specific path. So segment routing, this is another option. Another option for label distribution. This including also traffic engineering. So segment routing, you can also use the segment routing. Segment routing, shortest path routing. This is part one. Segment routing offers two kinds of transport labels. First, the label indicate that a packet should be forwarded. Number one. Number two is the packet to be sent towards the egress router via the shortest path using WSPAP or ISS. And LDP and segment routing both offer shortest path routing, but segment routing has two advantages. Label advertised in WSPAP or ISS, one less protocol to run, can be configured to use the same transport label at its home. So when you enable the segment routing under the WSPAP or ISS, no need to enable or no need to configure LDP or LSPP. So this is, you can say this is the advantage. Segment routing, shortest path routing part 2. This is basically same. Your packet traveling consideration is same. Push, then swap, last one is pop, then send packet. Same process. BGP level unicast. BGP level unicast. So considering here, this is one service provider. This is the one service provider. This service provider connect one customer. Customer 1. Customer 1, location 1. So this is another service provider connecting customer, same customer site B. You can say this is site 1 and you can say it's site 2. When this customer wants to communicate from C1 to C2 through this service provider and this service provider. So in that case, customer sending packet, this is the P router, packet, and this packet inserting the MPLS label. MPLS label is coming here. So MPLS label is coming here. This label value will travel through BGP to another provider router. This is called the BGP label unicast. BGP label unicast. Receive the BGP label unicast sending towards provider A's router, and this is
Sir,
normal
I have
BGP.
one question.
Okay.
You mean SBR3 to SBR4? That means this packet actually flow basically packet wise, not level wise.
Customer to provider, this is packet. Provider is to provider 2, this is label. This is label. This label is inserting in BGP, sending to another BGP neighbor. Okay. Encapsulate this label and insert the BGP session, and BGP will sending the label unicast family. BGP use the label unicast family to sending the label from ASBR 3 to ASBR 4. And again, this label is coming in provider S and sending packet to customer. Okay. So there is no MPLS here. BGP will travel level value, MPLS level value. BGP neighbor travel the MPLS level value through the label unicast family. Okay.
Thank you, sir.
So this is the BGP magic, not the MPLS magic here. This is the BGP magic. Static LSP. One filer method is static LSP. You can configure static LSP in your ingress or egress router, but it's rarely used in production. Static is more complex, like static routing. How many kinds of transport label does segment routing offer? There is 2. Transport label does a segment routing offer. What are the advantages of RSVP? Very fast protection from failure and automatic discovery of better parts in the network. What is an advantage of using segment routing? Does not require to run separate level advertising protocol. So this is basically our today's session. There's no configuration. So this is just a concept how to basically how to travel label from egress router to ingress router to egress router, and what is the role of provider router, what is the role of provider edge router, and what is the role of customer edge router. And there is some special level here, some reserve level here, 0 to 15, and some special level is explicit null, implicit null. So this is you can say totally BGP, MPLS level distribution mechanism, how it will work in MPLS domain. So I can say this is the summary of our today's topics. Okay, MPLS, the mechanics. So is there any question?
Sir, how they can choose the best route or which attribute actually works here?
Okay, best route by default, it's basically depends on which level distribution protocol you use in your production. If you use LDP, considering this topology, so you consider this router 1 is the ingress router and router 5 is the egress router. So this is the shortest path for IGP. It can be ISIS or it can be OSPF. So in MPLS, for MPLS level, if you configure LDP, ICP path copy, LDP copy the ICP path. Okay, no change the forwarding path. Okay, if you use RSVP, you can implement traffic engineering. But by default, if you yet not deploy any traffic engineering, by default RSVP also sending packet through the ICP next hop or ICP based path. Okay. All again you can say for segment routing. Also in segment routing, same thing will be happen. They use the ICP based path. If you configure the traffic engineering, then traffic engineering, when you configure, you can mention the next hop. You can mention the traffic engineering path in LSP. So if your defined LSP path, traffic will travel your defined LSP path. Okay, so it's basically user defined. If you use traffic engineering, then your traffic will be traveled through your user defined path. But by default, every protocol use ICP based path by default.
That means
Clear?
LDP.
By default, you can use LDP, you can use RSVP, or you can use segment routing. Everyone choose ICP based path by default.
Okay,
If you configure traffic engineering, then your path will be different. But LDP have no feature of traffic engineering. But RSVP and segment routing have. Clear?
yes, sir.
Okay. So I think that's all for today about this.